Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into a story about the death of stars and how such distant fires might touch the fragile surface of Earth. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who have already joined along, thank you. The journey begins in silence. Outer space is vast, dark, and nearly empty. Yet within this seeming emptiness, stars live out lives of remarkable contrast. Some shine softly and fade without much disturbance. Others end in quiet expansion, drifting into planetary nebulae, leaving behind white dwarfs that glow faintly for billions of years. But a few, the most massive, follow another path. Their end is not stillness but collapse, not a fading but a sudden and overwhelming release. This release is what we call a supernova. A supernova is not a single kind of explosion, but rather a family of endings. In one version, a giant star burns through its fuel until no further fusion can hold back gravity. The star's core collapses, and the outer layers fall inward, then rebound violently outward. In another version, a white dwarf in a binary system gathers matter from a companion star until it reaches a threshold, igniting a runaway reaction that tears it apart. Both outcomes are the same, a sudden brightening that for a short while can outshine entire galaxies. The irony is gentle but striking. The universe is mostly quiet and dark, yet when a supernova ignites, it produces as much light in a moment as all the stars of 100 billion suns combined. Another quiet irony is that such brilliance comes not from creation, but from destruction. A third is that these explosions, though unimaginably vast, occur in silence, for space itself carries no sound. Scientists study these events through light curves, spectral fingerprints, and faint traces of isotopes scattered across cosmic dust. The precise mechanisms of how core collapse rebounds, how neutrinos surge outward, and how energy transfers through collapsing layers are still subjects of study. Some mysteries remain unsolved, such as why certain supernovae appear brighter than models predict, or why some leave behind neutron stars while others collapse further into black holes. One poetic truth is that every heavy atom in the human body, every particle of iron in blood, every trace of gold in the crust of Earth, was born in these violent endings. The vast fires of dying stars created the elements necessary for oceans, rocks, and life itself. Without the death of other suns, Earth would be bare of the chemistry that allows it to breathe. The contemplation rests on time. These explosions may last only weeks in visible light, but their echoes spread across millions of years. A supernova from a star long gone might be travelling toward us at this very moment, its light and particles moving steadily across the emptiness. And when it arrives, it will not ask permission. It will not pause. It will simply appear in the sky, and Earth, in all its stillness, will become a quiet witness. A star's end begins slowly, almost without notice, in the balance between gravity and pressure. For most of its life, a star holds itself steady by burning hydrogen into helium, the simplest transformation that powers light. Over long stretches of time, millions and then billions of years, this burning keeps its shape fixed and its surface steady. Gravity presses inward, while the flow of radiation presses outward, an equilibrium that seems calm, almost eternal. But it is not eternal. The supply of fuel is finite. When the hydrogen at a star's core runs low, the balance shifts. Gravity begins to win, the star contracts, and under that pressure, helium fuses into carbon, carbon into oxygen, oxygen into neon, then into magnesium, silicon, and finally iron. The process is layered like an onion, each shell burning faster than the last. Hydrogen may take billions of years to consume, but the final steps pass quickly. Silicon burning into iron takes only a day. Iron is the limit, for fusing it consumes more energy than it releases. Once iron dominates the core, the star cannot resist collapse. The collapse is sudden. The core shrinks in fractions of a second, densities rise beyond comprehension, and in that crushing moment, the very protons and the electrons of matter combine into neutrons. A neutron star is born in the heart, compact and strange, a fragment of matter so dense that a teaspoon would outweigh mountains. The layers above this core fall inward, rebound, and with the aid of a storm of neutrinos, are hurled back into space as the star explodes outward. The energy released is so great that for a brief period, a single star can outshine every other star in its galaxy. The ironies linger in the stillness of these facts. The heavier a star is, the shorter its life, though it holds more fuel. The universe waits billions of years for fusion to build toward iron, only for the collapse to finish in seconds. And the brightest lights of the cosmos mark the moment of death, not of birth. Scientists still debate details of this collapse. Neutrinos, nearly massless particles that rarely interact with matter, seem to play a crucial role in transferring energy outward, yet the physics of their exact role is not entirely solved. Similarly, the fate of the remnant is uncertain. Sometimes the neutron star remains spinning and radiating. Other times, gravity pulls further and a black hole forms, erasing the core from view. In the silence of space, this drama unfolds without witness until light crosses the void. A supernova may occur in a galaxy 100 million light-years away, its glow reaching us after travelling longer than primates have existed. Or it may happen closer, within the fragile neighbourhood of Earth, where the difference between a spectacle and a catastrophe lies only in distance. The process is both common and rare. Thousands of supernovae have occurred in the Milky Way since life began on Earth, yet only a few have been close enough to be seen by human eyes. Their records survive in ancient writings. Chinese astronomers noting a new star in the sky that lingered for months, medieval monks sketching the Crab Nebula's light, modern telescopes capturing the collapse of stars in galaxies far away. Each sighting is a message from the past, telling of a star that has already died, its death delayed by the travel of light across vast time. And so, near or far, sudden or slow, the universe continues to cycle through endings. Each supernova adds a new layer to the quiet story of matter, a story written in gas and dust that will someday settle into new forms. In this way, death is never only loss but also passage, a momentary brightness before silence resumes. The life cycle of stars is long, patient and repetitive, yet within its patterns, variety emerges. In vast clouds of hydrogen gas, gravity gathers matter into knots. These knots grow denser, heat rises, and eventually the conditions reach the threshold for fusion. A star is born. The smallest of these red dwarfs may glow faintly for trillions of years, so stable and efficient that none have yet died in the age of the universe. The largest blue giants blaze brightly and exhaust themselves in only a few million years, vanishing long before even a single orbit of the Sun's spiral through the Milky Way is complete. The slow irony of this system is that size dictates fragility. The smaller the star, the longer it lasts, while the giants, heavy with fuel, spend themselves recklessly, living fast and ending quickly. It is a quiet reminder that in the universe, abundance does not always mean endurance. Another irony rests in the stars that end with almost no visible sign, fading into white dwarfs that cool for eons, while their massive cousins erupt violently, becoming cosmic beacons visible across galaxies. A third is that the stars that vanish silently outnumber the bright explosions, yet it is the rare, destructive ones that leave the deepest marks on history. Earth itself formed from the remnants of earlier generations, the carbon in forests, the oxygen in the air, the silicon in rocks, and the calcium in bones all trace back to stars that died long before the sun was born. The solar system is a second-hand creation, pieced together from stellar remains, a fact that lends a quiet sense of inheritance to every breath taken on Earth. Scientists classify stellar life cycles with precision. Main sequence stars burning hydrogen, giants swelling and shifting, white dwarfs cooling in silence, neutron stars spinning rapidly, black holes swallowing light. Yet within these categories, mysteries persist. Astronomers still debate how many massive stars end as black holes without visible explosions, collapsing inward so completely that only faint neutrino signals mark their passing. Others puzzle over the rare superluminous supernovae, explosions so bright they defy models, their causes not fully understood. In deep time, stars are not unique individuals but part of a cycle. Clouds collapse into stars, stars shed matter into space, and that matter returns to clouds again. Across billions of years, the galaxy breathes in this slow rhythm, scattering and regathering dust. Even the sun, stable as it seems, will someday expand into a red giant, shed its outer layers and leave a white dwarf at its heart. It will not explode, for it is not massive enough, but its remains will mingle with interstellar clouds, ready to form new worlds. From Earth's perspective, these processes are nearly invisible. The sky appears fixed, the stars eternal. Yet the records of ancient cultures remind us that skies do change. Bright new stars appeared in centuries past and then faded again, leaving behind nebulae that telescopes can now resolve. Each such record is a trace of stellar life cycles, witnessed for only a moment in human history, but unfolding on scales far beyond human time. In this stillness, it becomes clear. The life cycle of stars is both the most ordinary process in the cosmos and the most extraordinary. Ordinary because it repeats endlessly across billions of suns. Extraordinary because every stone, every leaf, and every living cell on Earth is bound to its rhythm. The cycles of stellar birth and death are the hidden architecture of existence, written not in words but in light. In the heart of every supernova, the forge of elements burns brighter than imagination allows. Ordinary fusion in stars creates helium. The collapse of a massive star, however, drives conditions to extremes. Temperatures soar to billions of degrees, pressures climb beyond comprehension, and in that crucible, new elements form. Gold, silver, uranium, and dozens of others are born in instants, scattered into space by the blast. Every atom heavier than iron on Earth, in soil, in mountains, in the human body, comes from such endings. The poetry of this fact is hard to ignore. The glitter of a ring, the copper of a coin, the iodine in salt, the calcium in a tooth, all trace their origin to stellar death. It is a reminder that beauty, utility, and necessity alike are gifts of catastrophe. The first irony rests here. Destruction is the only means by which the universe creates complexity. The second is that the heaviest elements, so rare and precious on Earth, are produced in enormous abundance for brief moments and then flung outward, destined to become trace materials on future worlds. The third is that these explosions, though unimaginably vast, have no intent, yet they provide the essential matter for life and civilization. Scientists understand much of the process through nuclear physics, yet mysteries remain. For example, whether all heavy elements arise from supernovae, or whether neutron star collisions are also required, is still under debate. Observations of kilonovae, the aftermath of neutron star mergers, suggest that such events may play a major role in producing gold and platinum. The proportions of contributions from different cosmic forges remain uncertain. Even so, the evidence is etched into Earth itself. Isotopic studies of meteorites show traces of material from supernovae that predated the solar system. Grains of dust older than the Sun carry fingerprints of stellar explosions and were incorporated into the planets as they formed. Within the crust and mantle of Earth, the history of stars lies hidden, unrecognized by the rocks themselves but revealed by science. The quiet irony of time deepens this truth. A star may burn for millions of years before its collapse, yet the creation of elements during the explosion takes less than a second. Billions of years later, those atoms find themselves in oceans and in cells, playing roles their origin could never predict. Like a planetary exhale, the supernova's breath disperses across the cosmos, settling into new patterns without design. The forge of elements links distant scales of existence. The collapse of a star light years away, eons ago, shapes the chemistry of living tissue today. The iron flowing in blood is kin to the iron at Earth's core, both created in ancient stars. The gold in a crown is cousin to the uranium deep in mountains, both products of stellar death. To think of this is to pause in wonder, not with drama, but with still recognition that nothing on Earth is separate from the life and death of stars. The calm of distance defines whether a supernova is spectacle or threat. In the wide vault of the galaxy, stars live and die continually, but most do so far beyond Earth's reach. A supernova exploding tens of millions of light years away can be seen with telescopes, yet it changes nothing here. A supernova thousands of light years away may appear as a brilliant new star in the night, brighter than Venus, casting shadows on the ground. But if the distance shrinks to only a few dozen light years, the difference is no longer one of beauty, but of hazard. The irony is subtle. In space, 100 light years is close. For Earth, it is unimaginably far. Yet that separation marks the thin line between harmless light and harmful radiation. Another irony lies in how little agency Earth holds. Orbiting quietly, the planet can neither prevent nor predict the timing of a nearby supernova. A third irony rests in perspective. Humanity marvels at distant explosions without concern, yet the same event nearer to home could alter life profoundly. Astronomers have calculated these thresholds with careful attention. A supernova within about 30 light years might strip Earth's ozone layer through gamma-ray bursts and cosmic rays, allowing ultraviolet radiation from the Sun to strike the surface unfiltered. At distances beyond 100 light years, the radiation weakens to negligible levels, leaving only a bright spectacle in the sky. Between those ranges lies uncertainty, where the severity of impact depends on the strength of the supernova, the alignment of Earth, and the resilience of the atmosphere. One poetic truth is that Earth may already carry evidence of such events. Studies of iron-60, a radioactive isotope produced in supernovae, suggest that debris from nearby explosions reached the solar system a few million years ago. Deposits of this isotope have been found in ocean sediments, like a faint fingerprint of a star's death recorded in the quiet seabed. Whether those events affected climate or life remains unresolved, but their trace is real, and it shows that Earth does not always stand apart from cosmic violence. The mystery endures. How many times in Earth's long history has life been brushed by the nearby explosions? Extinctions leave gaps in the fossil record, but causes can be difficult to separate. Impacts, volcanic eruptions, changing seas, shifting climates, each leaves a signature. And in that crowded record, the silent wash of radiation is hard to discern. It is possible that no major extinction was ever caused solely by a supernova, or it is possible that several were shaped by their influence. The archive of deep time does not offer a clear answer, and so distance governs the story. Most stars live and die far away, their ends adding to the galaxy's quiet rhythms without touching Earth. But a few, scattered through the neighbourhood of the Sun, remind us that the cosmos is not always a distant theatre. It is also a shared environment, where the fortunes of planets can be shaped by the fates of nearby suns. Light is constant, steady and finite in speed. It travels at nearly 300,000 kilometers per second, yet across the galaxy this is slow. When a supernova ignites, the brightness does not appear everywhere at once. It radiates outward like ripples from a stone in water, moving across space with unchanging pace. If a star explodes 1,000 light years away, Earth will not know until 1,000 years have passed. The event is already history by the time its light arrives. This delay adds a gentle irony. The night sky shows not the present but the past, a record of things already complete. A bright new star seen by human eyes is no longer burning. It is the delayed image of its death. Another irony is that a single flash, lasting weeks in stellar terms, can dominate the vision of Earth for months, altering calendars and guiding myths, yet the event itself ended long before its light was noticed. A third irony is that for all its speed, light is still too slow to make the universe immediate. Cosmic events are always remembered, never witnessed in real time. Scientists rely on this slowness to study history. Telescopes detect supernovae not only in the Milky Way, but in galaxies millions of light-years distant, each one a record of stellar death from long ago. Some are so far away that their light began travelling when early mammals were still small and unremarkable. Observing them is like peering through layers of time, a cosmic archaeology written in light. The uncertainty arises in what might be approaching even now. Somewhere in the Milky Way, stars are reaching their limits, collapsing, exploding, scattering elements into space. Their light is on its way, but Earth has not yet received it. At any moment, perhaps tonight, perhaps 1,000 years from now, the sky could shift and a new point of brilliance could appear. The precise star, the precise timing, remains unknown. One poetic truth is that light, though delayed, never loses memory. Even after a star is gone, its photons continue their journey, carrying the story forward. Dust and gas may absorb them, galaxies may bend their paths with gravity, but some reach Earth's atmosphere and enter human eyes, messages from a vanished past. In this way, the speed of light becomes both a gift and a veil. It allows the universe to be seen, yet it prevents the present from being known. Earth is always watching history, never the now. The cosmos, vast and indifferent, unfolds in impedance, and light carries its record patiently across gulfs of time. The sky has never been fixed, though it often feels eternal. In rare moments, a supernova becomes visible from Earth, and the night transforms. A point of light appears where none had been, brilliant enough to rival planets or even the moon. Shadows may stretch at night from its glow, as though the world has gained a second sun that only rises after dusk. Records of such events endure across cultures. In the year 1054, Chinese astronomers recorded a new star in the constellation Taurus, so bright it was visible even in daylight for weeks. Centuries later, telescopes revealed the Crab Nebula at that location, a ghostly remnant of the explosion. In 1604, Johannes Kepler observed another such star, now remembered as Kepler's supernova. Earlier still, in 1006, observers across the Middle East, China and Europe described a brilliant new point in the heavens, one of the brightest supernovae ever witnessed by humanity. For months, it outshone Venus. These records show how the cosmos occasionally intrudes into human history, leaving marks in chronicles, calendars and art. The irony of these events is gentle. To human eyes, the sky appears immutable, yet stars live and die within it continually. Another irony is that the most powerful explosions unfold in silence, the atmosphere carrying no sound of the blast. A third irony lies in memory itself. The human record of a supernova may last 1,000 years, while the event's light lingers only months before fading into obscurity. Scientific study reveals more detail than the naked eye could know. Modern telescopes see not only the remnant gas but also the rapidly spinning neutron stars at their centres, pulsing with radiation. The Crab pulsar, born in 1054, spins 30 times per second, a beacon that continues long after the explosion itself dimmed from view. These remnants are both grave markers and survivors, carrying forward the evidence of collapse. The mysteries remain in abundance. Why do some supernovae shine brighter than expected? Why do others fade too quickly? Astronomers still refine models, testing them against observation, seeking the physics that governs brightness curves and lingering light. Even with vast data, not all patterns are explained. One poetic truth is that a supernova seen from Earth is already a memory from deep time, its light delayed across centuries or millennia. The brightness that startled medieval astronomers had begun its journey when empires were rising and falling far below. Humanity records its presence as if it were sudden, but in truth the star had died long before its light reached human eyes. For Earth, such events are rare, scattered centuries apart. But in the galaxy they are common, occurring every few decades, sometimes unseen, hidden by dust. The sky of Earth is calm not because stars do not die, but because distance and obscurity conceal most of their deaths. The visible ones are simply reminders, glimpses into a universe where endings are routine and brilliance is temporary. Radiation is invisible, yet it carries the greatest risk from a nearby supernova. When a massive star collapses, gamma rays, X-rays and showers of high-energy particles pour into space. Light is the visible trace, but radiation is the hidden breath. If Earth lies within range, this unseen wave touches the atmosphere, a quiet brush that can have lasting effects. The process is well studied yet still uncertain in detail. Gamma rays strike molecules of nitrogen and oxygen, breaking bonds, setting off chains of reactions. Ozone, Earth's shield against ultraviolet sunlight, can thin or vanish under this pressure. Without it, the surface receives more ultraviolet radiation than life is adapted to endure. Some organisms may tolerate the shift, but many would suffer. Plants near the surface of the ocean, tiny phytoplankton that form the base of the food chain, could be especially vulnerable. Their decline could ripple upward into larger ecosystems, altering balances that had seemed steady. Here rests the first irony. Earth, with its rich life and protective air, is at once shielded and exposed. The atmosphere deflects countless cosmic particles daily, yet a single stellar death nearby could strain it beyond safety. The second irony lies in timing. A star may live millions of years in stability, only for its end to send harm across space in days or weeks. The third is that the most dangerous part of a supernova is not its visible beauty, but the invisible rays no human eye can see. Scientists model these effects with computer simulations, drawing on chemistry and climate data. They can estimate how much ozone might be lost depending on distance and energy output, yet uncertainty lingers. Would the damage last months, decades, or longer? Would climate shift in response, cooling as atmospheric chemistry changed? The answers remain incomplete. Earth's history offers few clear examples, only subtle isotopic clues in sediments and rocks that hint at past exposures. One poetic truth is that radiation, though invisible, leaves faint marks. Cosmic rays create isotopes like beryllium-10 and carbon-14 in the atmosphere, which later settle into archives of ice and sediment. These quiet records allow scientists to reconstruct past cosmic influences, though interpretation is slow and debated. In the vast scale of time, most radiation from supernova misses Earth entirely, absorbed by distance or dispersed across the galaxy. Yet the possibility remains that in rare intervals, Earth has been brushed by such breath, and life has adapted, endured, or shifted in its wake. Earth's atmosphere is a fragile skin, a veil of gases only a few tens of kilometers thick, yet it sustains all surface life. It regulates temperature, filters sunlight, and shields against cosmic rays. When a nearby supernova sends its flood of radiation, this veil is tested. Molecules of ozone made from 3 atoms of oxygen are broken apart by gamma rays and high-energy particles. The balance that normally repairs ozone can be overwhelmed, leaving gaps in the shield. The consequence is indirect. The supernova does not scorch Earth with fire. Instead, it allows the sun's ultraviolet light to reach the surface more freely. Plants and animals, accustomed to the filtered spectrum, find themselves under harsher rays. Skin burns more easily, DNA is more often damaged, and the delicate tissues of plankton, corals and seedlings absorb too much energy. What begins in the air translates into shifts in soil, sea, and living tissue. The irony of this process lies in its subtlety. Earth might orbit in sequence, unchanged in orbit and climate, yet invisible chemistry alters the foundations of life. Another irony is scale. A star dozens of light years away can influence the fate of microbes floating near the ocean surface. The third irony rests in resilience. While some species would perish, others would adapt, thrive, or seize new niches, turning catastrophe into opportunity. Scientists have modelled possible outcomes. A nearby supernova might thin ozone by half, lasting for years. On land, this could increase mutation rates and stress ecosystems, but in the ocean the effect could be greater. Phytoplankton, forming the base of marine food webs and producing much of Earth's oxygen, could decline. If their numbers fall, food chains ripple, fish stocks dwindle, and atmospheric chemistry shifts. Yet uncertainties remain. Would the damage be temporary with quick recovery or lasting reshaping evolution? Evidence from sediments is suggestive but inconclusive. One poetic detail is that deep oceans, caves and soil would remain shelters. Life in these places, already accustomed to low light or isolation, would barely notice the change above. In this way, Earth's diversity becomes a form of insurance, a web of habitats where extinction in one place does not erase life everywhere. The mystery persists. Have such events occurred before? Some mass extinctions in Earth's past show sudden losses, yet causes overlap. Volcanic eruptions, asteroid impacts, changing seas. The signature of radiation is harder to find, leaving scientists cautious. It is possible that life on Earth has already endured more than one nearby supernova, surviving quietly, its memory held only in the chemistry of ancient rocks. In the quiet balance of air and light, Earth continues. Most of the time the shield holds firm. Only rarely is it tested, and when it is, the consequences are neither instant nor total. Instead, they unfold slowly as ecosystems adjust, as some forms vanish and others emerge. The sky may look unchanged, but the invisible chemistry writes a story across millennia. The oceans hold much of Earth's memory. They cover most of the planet, deep and unbroken, moving in rhythms that respond slowly to change. When radiation from a nearby supernova brushes Earth, much of its effect is mediated by the seas. Water absorbs energy and disperses it, moderating extremes. Yet within the upper layers, where light still reaches, the story unfolds differently. Phytoplankton float near the surface, tiny yet abundant, converting sunlight into energy and releasing oxygen. They form the base of nearly every marine food web. If ozone thins and ultraviolet light intensifies, these organisms become vulnerable. Their delicate cells can be damaged, their numbers reduced. The chain of consequence is quiet but far-reaching. Fewer plankton mean fewer fish, fewer seabirds, and altered cycles of carbon exchange with the atmosphere. The seas that appear changeless from above are in fact deeply sensitive to the chemistry of the sky. The irony lies first in scale. Stars dying far away can disturb microbes adrift in waves on Earth. The second irony is that the very organisms most vulnerable, the plankton, are also those that produce much of Earth's oxygen, linking stellar death to breath itself. A third irony is that the vast oceans, seemingly inexhaustible, depend on invisible layers only meters deep, where the balance can shift quickly under radiation. Scientists explore this connection through modelling and sediment cores. Layers of ancient seabed contain isotopes, microfossils and chemical traces. Among them is iron-60, a short-lived isotope that betrays supernova origin. Its presence in deep ocean sediments hints that Earth has already been showered with stellar debris in the recent geological past, perhaps 2 or 3 million years ago. The traces are faint, yet they serve as reminders that the oceans are both archives and shields, storing evidence of cosmic events that the land forgets. Still, mysteries remain. Did these past exposures shift climates or alter ecosystems? Some argue that minor extinctions in marine life could align with such events, but proof is elusive. The records are layered with signals from volcanism, impacts, and shifting currents, all overlapping. Separating the voice of a supernova from this chorus is a challenge scientists continue to pursue. One poetic truth is that the oceans respond slowly, their vastness smoothing short-term shocks. Even if radiation thins ozone and stresses surface life, deeper waters remain stable. Life finds refuge in the dark where ultraviolet rays cannot reach. Evolution may be nudged rather than broken, reshaping rather than erasing. In this way, the seas embody resilience, not untouched, but enduring, their memory carried in sediments and the persistence of life in shadowed depths. And so the oceans remain both witness and buffer. They absorb, they remember, and they continue. Beneath the surface, currents flow unbothered by the silence of distant stars. Above, waves rise and fall, as they have for billions of years, carrying forward the patient rhythm of Earth, even under the quiet breath of radiation from the cosmos. Life on land depends on the sky above it. Plants grow by sunlight filtered through the atmosphere, drawing carbon dioxide from the air and releasing oxygen back into it. Animals breathe, feed, and shelter under the same protection. When a nearby supernova alters atmospheric chemistry, the vulnerability of terrestrial life is exposed. Increased ultraviolet light, reaching the ground more intensely, changes the quiet routines of forests, grasslands, and deserts. The effects would not be dramatic fire or sudden destruction, but gradual shifts. Leaves might show more damage, growth stunted by excess radiation. Seeds and seedlings, most delicate at the start of life, could fail in greater numbers. Animals depending on plants for food would notice the decline. Skin and eyes of surface creatures exposed directly to the sun would suffer more. Even in this, resilience is uneven. Some species adapt quickly while others falter. The ironies emerge gently. The first is that land, though seemingly firm and secure, is more exposed than the deep sea. The second is that ultraviolet radiation, normally tamed by ozone, is both giver and taker, essential for processes like vitamin formation, yet harmful when unchecked. The third irony is that survival may depend not on strength but on chance, with shaded environments and nocturnal habits offering unplanned advantages. Scientists have examined extinction events in the fossil record for signs of such stresses. Some minor die-offs, particularly among shallow water organisms and land plants, raise questions about whether radiation played a role. Yet certainty is elusive. Volcanism, impacts, and climate shifts all leave clearer signatures. Radiation, invisible and fleeting, leaves little mark beyond chemical isotopes. This absence of clarity remains a mystery. Has Earth endured nearby supernovae without record, their influence hidden within the background of other catastrophes? One poetic truth is that even in times of stress, life seeks refuge. Forest understories, caves, burrows, and soil offer shelter. Small organisms may endure where larger ones perish, and niches can shift in unexpected ways. Evolution works quietly, turning disaster into change, ensuring that while forms vanish, life itself continues. From a geological perspective, these trials pass quickly. A few thousand years of stress might seem long to species but short to continents. Sediments layer, climates shift, and ecosystems recover. What once was crisis becomes another chapter in the long record of adaptation. Earth's surface, fragile yet enduring, absorbs the influence of distant stars and continues forward, reshaped but not undone, and so the land remains. Grass sways in wind, trees cast shade, animals move through their habitats, and the cycles of day and season continue. Above them, the sky holds the quiet potential for change, yet most days it is simply blue by day, star-dotted by night, steady and familiar. The influence of distant suns, though possible, is rare, and Earth lives mostly in calm, its surface a place of ordinary rhythms under extraordinary skies. Stone remembers what life forgets. While plants and animals vanish without record, rocks and sediments hold faint traces of cosmic events. Deep in the seabed, layers accumulate slowly, grains settling year by year, preserving chemistry like a diary of time. Within these layers, scientists have found isotopes not native to Earth, fingerprints of nearby supernovae. One of the clearest is iron-60, a radioactive form that decays over a few million years. Its presence in ocean crusts and sediments shows that stars have died within a few dozen light-years of Earth in the recent past. The quiet irony here is that the seafloor, silent and dark, holds a better record of stellar death than the sky, which forgets its own flashes once light fades. Another irony is that isotopes born in fire and destruction become evidence of calm research in laboratories millions of years later. A third rests in time itself. Human science has only recently gained the ability to detect these traces, though they have been waiting patiently in stone for ages. Geological memory is not confined to isotopes. Certain anomalies in fossil layers, where sudden extinctions appear without obvious terrestrial cause, raise questions of external influence. Though impacts and volcanism explain many, the possibility remains that some shifts were driven by radiation from nearby stars. This hypothesis is difficult to prove, for cosmic signatures are faint and often erased by Earth's own restless geology. Yet the presence of supernova-borne isotopes strengthens the case that stellar events have brushed the planet more than once. The mystery deepens with timing. Some isotopic signals appear to align with minor extinctions, but correlation is not causation. The geological record is imprecise, layers blurred by erosion, mixing, and uneven deposition. It is possible that supernovae have influenced life in ways too subtle to isolate. It is equally possible that they have caused no major extinction at all, their influence drowned out by more immediate terrestrial upheavals. One poetic truth is that Earth itself is a palimpsest. Oceans deposit, mountains rise, glaciers scour, and volcanoes bury. Through all this, faint cosmic messages persist in fragments. They remind us that Earth is not isolated, but part of a wider galactic environment where even distant stars leave marks. And so, the stones keep quiet watch. They do not speak of light or brilliance, but of particles embedded in silence. To walk upon land is to step over records of cosmic fire, unrecognized beneath feet, yet present. The Earth is an archive not only of its own volcanoes and impacts, but also of the breath of dying stars. The traces of supernovae in Earth's geology raise a question that has no settled answer. Have these stellar deaths directly caused extinctions? The fossil record holds many sudden losses, yet the causes are often tangled. An asteroid strike marks the end of the dinosaurs. Massive volcanic eruptions coincide with the Permian die-off. Shifts in climate, ocean circulation, and atmosphere ripple through time. Among these, the influence of radiation from a nearby star remains more difficult to prove. Some scientists suggest that certain minor extinctions, especially those affecting marine plankton and shallow water species, may bear the signature of increased ultraviolet radiation following ozone depletion. Others argue that the timing is uncertain, that the resolution of the fossil record is too coarse to isolate a single cause. In this, the mystery persists. Perhaps no extinction can be traced solely to a supernova, or perhaps several were shaped by them, their fingerprints hidden beneath layers of overlapping signals. The ironies rest gently here. The first is that life's greatest changes may come not from Earth itself, but from distant stars, silent and unseen. The second is that science, so precise in measuring isotopes and radiation, cannot yet resolve events that unfolded millions of years ago with certainty. The third is that while extinctions seem catastrophic in the moment, they open niches for new forms, so that stellar destruction may have indirectly guided the path of evolution. One poetic detail is that evidence of supernovae lies not only in sediments, but also in the biology of Earth itself. Life has endured waves of radiation, adapted, and carried on. Each lineage alive today has ancestors who survived past trials, whether volcanic winters, impacts, or brushes with cosmic rays. Survival itself is a record, written not in stone but in genes. The debate continues. Some argue for links between supernova isotopes found in crusts and climatic shifts in the Pliocene. Others point to unexplained minor extinctions as possible outcomes. Yet proof remains elusive. The stars do not leave signatures on bones, only whispers in chemistry. The archives are incomplete, and mysteries remain. In this uncertainty lies a quiet truth. Not everything can be explained. Earth carries scars of fire, water and sky, but their stories are interwoven. To separate one from another is difficult, and perhaps impossible. The influence of dying stars may be one thread among many, subtle and inseparable from the rest. And so the question remains open. Perhaps no species has ever been lost solely to a supernova. Perhaps many have. The Earth does not answer, and the stars long extinguished remain silent. The debate itself becomes part of the record, a reflection of humanity's attempt to understand forces that shaped life long before humanity existed. Creation and destruction are never fully separate in the universe. The same explosions that strip atmospheres and stress ecosystems also create the very elements that make life possible. The iron flowing in human blood carrying oxygen through veins is the product of a collapsed star. The gold buried in mountains, mined for beauty and trade, was forged in a fraction of a second during a stellar death. Even the iodine in oceans, essential to health, traces back to cosmic fire. The first irony rests here. Life depends on catastrophe. Without stellar explosions, Earth would be a world of hydrogen, helium, and little else, a barren sphere without complexity. The second irony is that the same radiation that threatens to erase life is also part of the process that made life possible in the first place. The third irony is that destruction in one moment plants the seeds for creation in another, bridging eras with no intention, only physics. Scientists call this process nucleosynthesis, the forging of new elements in stars and their explosive ends. Observations of spectra confirm it, showing the fingerprints of heavy elements in supernova remnants and in ancient stars enriched by past explosions. Yet mysteries endure. Some isotopes are not fully accounted for, their origins debated between supernovae and neutron star collisions. The precise balance of contributions remains unresolved, leaving space for further discovery. One poetic detail lies in the way these elements are scattered. They drift outward into interstellar space, joining clouds of gas and dust. Over millions of years, gravity regathers these materials into new stars, new planets, and new chemistry. The galaxy breathes in cycles. Stars are born and live, die, and seed the next generation. Every planet, every ocean, every living being is a chapter in this quiet circulation of matter. The story is not one of progress but of repetition. Elements forged in fire spread, gather, and spread again. On Earth, they take form as mountains, rivers, forests, and flesh. In another system, they may remain as stone alone, never shaping life. The cosmos does not choose its outcomes. It only circulates its materials, indifferent to what forms they take. And so the ironies rest in plain view. The human body, fragile against radiation, is itself built from the remnants of such radiation-born atoms. The planet's riches, mined and shaped into tools, ornaments, and machines, are gifts of ancient deaths. The sky above, calm and distant, is a constant reminder that every life depends not only on the sun that shines now, but also on stars that ended long before Earth began. Time stretches long beyond human scale, and in this expanse the fate of stars and planets becomes background rhythm. Supernovae erupt rarely in the Milky Way compared to the number of stars, perhaps a few each century, though most are hidden behind clouds of dust. For Earth, the chance of one close enough to matter is small, yet not zero. The galaxy is wide, stars are many, and even rare events eventually arrive. If such an explosion occurred within dangerous distance, Earth would not shatter. No fireball would sweep the planet. No sudden end would come. Instead, the influence would be slow, invisible, and lasting. The thinning of ozone, the rise of ultraviolet light, subtle stress on ecosystems. Life would bend, adapt, or in some cases vanish. The planet itself would endure, carrying on its slow tectonic drift, its cycles of water and air. the ironies remain steady. The first is that Earth, though so small in the galaxy, is vast enough to absorb even cosmic stress without ending. The second is that the universe, seemingly hostile in its scale and violence, is also the provider of every atom that makes survival possible. The third is that, in the end, Earth is neither central nor exempt. It is simply one world in a galaxy where stars live and die as they always have. Scientists search the skies for nearby stars approaching instability. Betelgeuse in Orion, bright and massive, may one day collapse in brilliance, though likely too far to threaten Earth. Others may be less famous, hidden, and their fates uncertain. The mystery endures. When and where will the next visible supernova appear? No telescope can predict the exact moment. The universe keeps its timing hidden. One poetic truth is that Earth itself will not last forever. The Sun, though too small to explode, will swell into a red giant, consuming inner planets and leaving behind a white dwarf. Long after, the galaxy will continue its quiet cycle of births and deaths. In that future, new stars will shine with atoms once carried by the Earth, scattered outward into interstellar clouds. And so Earth drifts in the present moment, fragile yet enduring under skies filled with both peril and promise. Most nights pass without change, the stars appearing fixed and eternal. Yet woven into that calm are the memories of past explosions and the certainty of future ones. The universe continues, patient, vast and silent, while Earth rests within it, a small witness to the endless cycle of light and darkness. The rhythm slows now, the story of stars settles into silence, and Earth drifts again beneath a sky that appears calm. The cycles of birth and death in the galaxy stretch over millions of years, far beyond the measure of a single night. From the surface of Earth, the constellations shine as if unchanging, their quiet patterns steady against the turning of the planet. The atmosphere, thin and protective, rests around the globe like a veil. Oceans breathe slowly, carrying heat and salt across basins. Forests exhale oxygen. Deserts stretch in stillness. Mountains hold their weight in stone. Every detail of Earth continues in its own rhythm, untouched in this moment by distant suns. The memory of past supernovae lies hidden in sediments and isotopes, yet the present is calm, the sky clear. Above, light travels endlessly, photons carrying the record of ancient stars across the void. Some arrive tonight, striking air and water, glancing from leaves and stone. Others continue past Earth, unobserved, their journey unending. In this slow exchange, the planet takes its place as part of the wider universe, not apart from it but woven into its fabric. The iron in blood, the calcium in bone, the gold in rock, all carry silent testimony that Earth is already the child of stars. Nothing more is needed, for existence itself is the gift of ancient fire. There is no urgency here, only the unfolding of cycles larger than imagination. The pace quiets further. No forward motion, no anticipation, only rest. Earth turns beneath the stars as it has for billions of years. The galaxy continues its slow breath. Light drifts through space and the silence deepens.